This is the Chapter 12 Mathcast. It contains 2 sections and 4 lessons. There have been many regression problems woven throughout the review-preview problems since Chapter 2, and this section is another opportunity to review the concepts and vocabulary. Students will explore the sampling distribution of the slope of a least squares regression line, and the conditions for inference are developed. The connection between the slope and the correlation coefficient is further explored. And finally, the students carry out confidence intervals and hypothesis tests for the slope of a least squares regression line. Now that the students have worked with many various sampling distributions, it should come as a natural conclusion that many examples of paired data they've worked with also represent samples. So the statistics they calculate from them, such as slope, intercept, and the coefficient of correlation, have their own sampling distributions. In Lesson 12.1.1, in the context of a coffee growing experiment, students develop the conditions for regression inference and learn to interpret commonly formatted computer output for the standard error of sampling distributions for the slope. In Lesson 12.1.2, the coffee plant experiment continues. Students realize that a beta of 0 would mean that knowledge of the explanatory variable fertilizer does nothing to indicate the value of the response variable yield per plant. If the population slope beta is 0, then the population value of the coefficient of correlation rho is also 0, by this familiar relationship from Chapter 2. And the null hypothesis in symbols, representing no relationship between the variables, would be rho is equal to 0. Problem 12.10 then steps the students through a confidence interval calculation on the slope, while problem 12.12 introduces the hypothesis test. The computer output for the coffee experiment is shown as being incomplete. The students are required to use algebra to find the missing values in problems 12.12b and 12.13b. This will require the use of formulas involving the t-statistic. These formulas can be reasoned from the general form for any standardized value, but the students may need some prompting to see this. And you may want to refamiliarize yourself with the necessary calculations before class begins. Section 12.2 introduces some common nonlinear models. Students have been using residual plots to determine if a linear model is the most appropriate fit for a set of bivariate data since Chapter 2. In this section, students have the opportunity to explore modeling techniques when there is some type of curved model that would fit the data more appropriately. Lesson 12.2.1 focuses on 2 different styles of quadratic models in the common quadratic situations of areas and acceleration due to gravity, while encouraging students to look for familiar curved underlying mathematical relationships first, rather than just trying out different curves blindly. Problem 12.19b points out that the more general quadratic equation, commonly used in calculators, is not the preferred form in this course because we want to restrict our focus on just 2 coefficients, a and b. And the now infamous chemistry teacher Mr. Knowlson makes his final appearance with some experimental data in problem 12.22. Lesson 12.2.2 highlights the exponential and power models, exploring 2 common ways to use logarithms to straighten data. You will want to be ready to provide prompts and guidance for the logarithmic transformations in this lesson. Further, logs of any base, such as base 10 for the common log or e for the natural log, will work. The subtly curved dry ice data returns from problem 267, and this time students will be able to fit a curved model to the data. Congratulations! If you've covered this and all previous chapters, you have completed the entire AP syllabus. Chapter 13 is an extension beyond the AP subset and explores ANOVA and some non-parametric tests.